In this section of our lecture, we're going to do the setup for our lab in this module. And I first want to address this idea of tributary areas. This project is really going to look at how we think and have discussions with other people about what we want to create and accomplish in our building. And one of the things we commonly do as architects, in at least our initial structural analysis, is to look at how loads are carried from our roof and floor systems and our wall systems down into our foundation systems. And we're really basically talking about gravity loads at this point, not seismic loads and or wind loads, because those would be lateral, at least in the case of wind load. Once again, as hopefully a review at this point, a uniformly distributed dead load or live load as calculated applied upon a structural system. So we have the orange as the load. We have a beam system transferring loads to a column system. And our next step is to resolve that down to loads. Before we get to loading the column itself, we resolve it to loading the beam system, so we can look at the deflections and the stresses, the shear and moments that are implied upon them. And this is a good graphic because it shows you this idea of how the tributary load is being applied to the individual elements. And so in this case, we're looking at larger loads applied on the inner members. And it's clear because there's more tributary load implied upon them. So we're going from the middle section of this floor to the middle section of this span of the floor. So there is twice as much implied load on this, on this beam as there is on this external beam, because we're only adding up the area from the midsection out to here, and obviously there's no tributary loads coming from the external part of the building. Just a reminder, in a hyperlink, this takes you out to a site which allows you to, for your specific address, find out the wind loads, the snow loads, so that you can start to set up seismic loads. You can start to set up your project's parameters and include those in your design and development calculations. So in our project, we're going to look at a specific Renzo piano building, but this project started well before that, a few years ago, as looking at our engineering building as an infill project where we created a superstructure with some columns to carry loads. And I'm outlining this because this is the basis of our thinking, and I've really kind of expanded it to really give you an opportunity to do some a closer look at a real-world project and some of the issues that might revolve around that. So here we have a roof view of that. We have the idea of live loads and dead loads applied on it and coming up with a value system, and then taking its overall tributary area to come up with a total load in that area. And then taking another look at that roof load, specifically as it's carrying down through the column systems as a tributary load. And we can do a lot then to figure out the sizing of certain elements, especially things like columns, where we care about how large they look and whether they have capacity. And so there are charts. This one is hyperlinked. This will take you out to a chart that a series in a book that gives you all kinds of different shapes of hollow section steel, and you can then, by knowing the effective length of your column, find out the load that it can bear within a certain safety factor to appropriately size your element. So let me go back to this presentation now. The one thing you have to really know to use this chart correctly is this concept of effective length, that K value, and that has to do with the way the columns are connected at the top and the bottom. And in many cases, so if they were rigidly connected to the frame and the foundation, they can actually behave stiffer. And if they're pinned, this is the basic unity value system, of the idea being that this is how mostly the pin connection is, the way we assume a column system would perform. So our K value would be 1. So also we'll look at beam systems, and this is, I don't know if this will go out. It doesn't go out. I have this hyperlinked in other parts of the slide presentation that we've already covered, where we can actually look then at the deflection of our beam system that's carrying a uniformly distributed load. We'll be able to set up our load here, our span, establish our pinning conditions, and then calculate our deflections. This is the project that we're going to look at, Renzo Piano. This is in Chicago. Let me just get over to the listing of this. I'll drag this onto the screen. This is the Art Institute of Chicago and the Modern Wing. So you can do any kind of Google search and find all kinds of great images of this project. I've selected this project because of the nature of this exposed structural steel, the louver systems, the column systems. I think there's all kinds of interesting ideas about what might be going on in this system. To have a discussion with a structural engineer. The aesthetics to me are very important, how thick these members look, how slender the columns look, all of the issues that might be involved with that kind of an evaluation. Let me get that out of the screen area. So there was a lot I did a little bit of research like through the construction drawings to get some details so you can see this idea of the sections of the steel on this roof superstructure, the louver system. We're going to build a lot of these. We're going to make the column, we're going to make the beam elements, and we're going to make this gridded system that fits into it. Another nice detail of this. And we're concerned with the kind of loads, looking at this as a beam load, looking at this as a column load, trying to figure out the tributary areas that are being carried down through that system. And this is a view from the rear of that building. So there's more of these slender columns. So I tried to do some from these, I tried to come up with just some, thumbnail sketches that we can use in our model. You can see the grid layout of the system. I tried to do an aerial shot of it and then get an idea of kind of like to scale it. So in my drawing, my scaling is just working from a Google Maps. And that's really the setup for this project then. So we're going to go through and do some evaluations with this. You'll get a great experience with just modeling these kind of unusual structures. It's relatively simple, but I'm trying to incorporate a lot of parametric components within this so you can make these easily adjustable to modify and then to look at the model and see what happens when you change those elements. So I'll conclude that and we'll look at diving into the project.